Hi everyone, and welcome to class number 37 of Physics 218. So last time we began talking about atoms and atomic spectra. We began our discussion of the Bohr model of the hydrogen atom that combines some classical physics with some quantum ideas like the de Broglie wavelength. And where we ended last time was in calculating the radii of the allowed electron orbits for the hydrogen atom, and it goes like n squared and some fundamental constants. Today what we'll do is we'll finish our discussion of the Bohr hydrogen atom. Our principal goal, and Bohr's principal goal, is to be able to calculate the energies of the atom so that we can go and predict the hydrogen spectrum. We'll also take a look at what the Bohr model implies about angular momentum quantization. After that, we'll take a short look that will introduce us to quantum mechanics in 3D and some new features so that we're then prepared to look at the hydrogen atom in quantum mechanics briefly on Monday. So I'd like us to start off by thinking about a whiteboard exercise where you think about the potential energy for a proton and an electron, aka what we have in a hydrogen atom, as a function of the radial separation r between the charges. So these are ideas that are hopefully familiar from Physics 118. So you might remember that the potential energy for two opposite charges looks something like this, and takes on this form. It goes like 1 over r. A few things that I wanted to mention. So first of all, there was a question on a reading quiz, I think the other day, about sort of the convention of where we set the zero of potential energy. From the form that we've written down, you can see here that u is 0 at infinite separation. Now this is somewhat arbitrary, but it's typical convention in E&M for a good reason. And to me, this is, there are several reasons why. First of all, it's only because we assume that u is 0 at infinity that you can write the potential energy down in this nice form. Otherwise, there'd be an additive constant. But the other thing, and to me the more physical reason, is the following. We associate potential energy for a system as having something to do with the interaction between two things in a system. That's how, for instance, in 117 we defined gravitational potential energy, right? Which is associated with the gravitational interaction between, let's say, like the Earth and, like a ball or something. You know that in electrostatics, right, Coulomb's law says that the force between two charged particles goes to 0 as r approaches infinity. So at infinite separation, you have no interaction. Since we associate potential energy with an interaction, it makes sense to set u equals 0 where there is no interaction, in other words, at infinity. One other thing that I want to comment on is the sign of the potential energy. Notice that it is negative. Now there's a bunch of ways you can think about this, and I'm not entirely sure how you thought about signs for energy in like 118. So one way that you could think about it, remember that that changes in potential energy, right? You can think of as minus work done by interactions that are internal to a system, so this W minus W internal, right? And so if you imagine starting right with sort of two charges that are infinitely separated, right? The plus charge and a minus charge feel an attractive force. So if that interaction is internal to the system, right, as like when you let those charges go, right, there's going to be positive work done internally, which means that delta U should be negative. Another way you can think about it, if it's easier, is sort of if you start with right. If you start with two opposite charges that are at a finite separation, and you want to separate them to infinity, right? You're gonna have to use, as some outside agent, are going to have to do work on the system to change its energy. If you have two opposite charges that are attracted, right, to each other, if I try to drag these things apart, right, you, the external agent, have to do positive work, which is going to tend to raise the potential energy of the system, which is consistent with this picture. However, it's easier for you to think about it. If the sign is confusing, please let me know, and we can talk about that in some more detail. We are now able to answer the following question. What is the energy of the hydrogen atom when the electron is in the nth orbit? And so we can write down this energy, and I'll call it E sub n because it depends on being in the nth orbit. I'll write this as a sum of kinetic and potential energies. So K plus U, and if you haven't noticed, I'm following Knight's notation here and writing U for potential energy, even though when we've been working out of Townsend, we've been writing V for potential energy. I think it'll be fairly clear in context what letter stands for what. Okay. Now we already dealt with this piece over here, right? So the kinetic energy, you know what that is. That just goes like, well, let's just fill this in. So we know that this is minus 1 over 4 pi epsilon naught E squared over R sub n, because we're in the nth orbit. Now our kinetic energy, you know, we're assuming the proton is fixed, so this is the electron's kinetic energy, and that's the electron mass here, right? That's just 1/2 mv squared. But what's helpful is that we already know from doing the Newton's second law analysis we began the Bohr atom discussion with. We already have something that's quite close to this. So, namely, remember from Newton's second law, right, we have, right, mv squared over r sub n. So this is mass times the magnitude of the centripetal acceleration was equal to the magnitude of the Coulomb force. So E squared over r sub n squared. Notice that this is close to 1/2 mv squared. If I just multiply both sides of this by r sub n over 2, right? So if I do that multiplication, so I cancel this r sub n and multiply by 1/2. If I do that, then I get 1/2 mv squared. And then now I'm going to get a factor of 2 downstairs, so this becomes a 1 over 8 pi epsilon naught, and I knock out a factor of r sub n. Okay, so now, right, if I take that and slide that back in here, right now I have 1 over 8 pi epsilon naught E squared over r sub n minus 1 over 4 pi epsilon naught E squared over R sub n. Good, we've got two terms that have a really similar structure. And now we are able to conclude that, so we have this term is half as big as that term. We're going to end up with minus 1 over 8 pi epsilon naught e squared over r sub n, right? And the negative sign of this energy, right? So notice that again, the energy will go to 0 as r sub n goes to infinity. And the energy is negative for a finite r sub n. That means that in order to take my electron from finite separation and move it to infinite separation, I'm going to have to add energy or do work to the system, which means that the electron and the proton really are attracted to each other, or in other words, the atom is stable. Okay. So we've got this now, and then the last thing we need to do is put in what we know about the Bohr, the radii. So now use result about the radii, and then if I plug all of that in, let's see, we have a minus 1 over 8 pi epsilon naught e squared, and then we have r sub n from last time, so 1 over that will give me an m e squared upstairs, and an m squared h bar squared, 4 pi epsilon naught. And so we've now got the E sub n in terms of only fundamental constants. Let's clean this whole thing up. So we have E sub n then equals a minus, we have m e to the fourth upstairs. Downstairs we have 8 times 4 is 32. 2 factors of pi squared. We have epsilon naught squared and h bar squared. Yep. And then times 1 over n squared. Okay. Now this is our result. This is this big lump of constants in front. Often it's convenient to work with its numerical value in electron volts. You can go and convince yourself that this really does have units of energy, all of this stuff. And so oftentimes we'll write this as minus 13.6 electron volts over n squared. So this is our main result for the energies of the hydrogen atom, or the Bohr energy levels. And so what's really important about this is that we've been able to apply sort of physical principles and get this result. This type of relationship for the energies was originally worked out just on purely empirical grounds. So there was spectral data, and people were able to look at it and infer that there's this pattern of stuff going like 1 over n squared. But that was just messing around with numbers. So what's exciting about what Bohr did was to be able to put that on some kind of, at least some semi-firm physical basis. So let's now sort of summarize graphically what the analysis of the energies gave us, and see how that can be applied to spectra. So as I said, the energy of the atom is negative. So this is E equals 0. And this represents sort of our atom being ionized. Sort of what that is that the electron and the proton are completely pulled apart, and this right is going to be in the limit as n approaches infinity. Now, as we saw, right, the energies are negative, so we have right something like down here, we have n equals 1, right, and that's minus 13.6 eV. So I have to put in 13.6 electron volts to completely rip the electron out of a hydrogen atom. And then the other levels are spaced like 1 over n squared, so they get closer and closer together as n increases. So it might look something like this. So let's think there is a better drawing of this in your reading, but we'll sort of go something like, and etc., and that continues onward. So this now lets us be able to predict the lines that we might see in, say, an emission spectrum. So, for example, right, we might ask the question of what wavelength is emitted in a transition going from n equals, what shall we do? We'll do n equals 6 to n equals 3. Okay, so let's draw that here. Actually, let me see if I can do a couple more lines. 4, 5, and something like that. So going from 6 to 3 is going to look something like this. Okay. And so we can calculate this in the following way, right? So first, right, we know that in sort of the Bohr picture of atoms, right, this transition from n equals 6 to n equals 3 is associated with the atom emitting a photon whose energy is equal to the energy difference between these two levels. So the photon energy, and I'll abbreviate that E sub pH, it's going to be the energy of the higher level state minus the energy of the lower level state. And that's going to be E, so 6 minus E3. And then we can just calculate that using using the result from the Bohr model. It's often easier to just use 13.6 EV rather than sort of plug in all the constants, although you can certainly do that. So we have, so it goes like n squared, so we have 6 squared here. Then we have a minus or a plus, so minus 13.6 EV over 3 squared. And if you go and plug the numbers in for that, what I get is about 1.13 electron volts. Now, you can convert this photon energy into a wavelength, right? Because you know that, right, E of a photon goes like hc over lambda, right? So sort of combining sort of Einstein's postulate about energy of photons with the relationship between wavelength, frequency, and light speed. So that means that, right, my lambda equals hc over E of my photon. And then it turns out to be useful to use h in electron volt seconds. We just have to be careful about tracking our units. But if we're careful, that's going to be fine. So H in electron volts is going to be 4.14 times 10 to the minus 15. That's like a 5. Minus 15 electron volt seconds. And then, so since we have an energy in electron volts, that'll cancel. So we have, right, 3 times 10 to the 8 meters per second here, divided by 1.13 electron volts. Let's check, right? Electron volts cancel. Seconds times 1 over seconds. We do, in fact, have meters here. And so that leaves me with a wavelength of 1096 nanometers. So something in the near infrared. So now I'd like you to think about a clicker question that's sort of related to this. So let's turn to that now. So hopefully you had the chance to think about comparing a transition from n equals 7 to 2 to to going from n equals 6 to n equals 2. And hopefully you can sort of like visualize from like this kind of diagram that if I go from 7 to 2 versus 6 to 2, 7 to 2 is going to give rise to a higher energy photon. So if I have a higher photon energy from the work we just did, you see that we'll have to have a shorter wavelength associated with that. So now that we've done that, let's have you try one more exercise where you'll be able to predict the visible wavelengths in the hydrogen spectrum, and the solution is going to be in the class slides.